In this video, we are going to demystify big O notation. That means we're going to talk about time complexity and space complexity. Now, why do we actually need this? Well, think about the algorithm as a trip you are planning and the data structures that you are going to use for solving that algorithm as the vehicle that you are going to choose. Now, let's say you're moving from A to B. You could just take your bike and ride it to a B location. That will take a roughly amount of time. That's fine. But if you take the car, it will take you less time. Or if you take the airplane, it will take you even less. So think of algorithm data structures like this. Data structures are the vehicle that you are going to use to solve those algorithms slash the trip that you are going to take. Now, different trips are going to use different vehicles. Different vehicles have their upsides, their downsides. So you are going to choose the best that you can have for that particular trip. Now, let's just go into some details and let's talk a little bit about what type of O notations, time complexity we might have. And just a quick note before we get into this chart even deeper. There's time complexity and space complexity. Basically, space complexity does have these O notations also, but it means how much space it will take to actually solve that algorithm. So maybe you are just going to sort in place. That will not take up any extra space, but maybe you are going to duplicate an array, or maybe you're going to create a new hash map that will take a new space, and that's what we are going to add with categorize with big O notation. Now, there's a lot right over here, I know, if you are not familiar with this, but we're going to take it one step at a time, and we're going to also have some analogies. So the fastest one and the most sought after one is constant time. So this green line over here, that's big O of 1, which means that it will take basically no time at all, no extra time at all for the algorithm to run. Now, a word of caution right over here, we are not measuring time in seconds or hours or weeks for that matter. We are having this kind of time approximation. Does it take, is it instant? Is it constant? Is it logarithmic? We are going to talk about them later on. So this is basically instant. Think about, let's say, a list, and you want to grab the first item in that list. It doesn't really matter in terms of how much data is in that list. It could be 10 elements, there could be 100 or 1 million elements in that list. Taking the first element out is going to take constant time. So each and every time, regardless of the size of the input data. That is constant time. Now, here comes logarithmic time. We're going to talk about that in just a second, but the easiest way to understand logarithmic time is to just understand first the constant time. So, the linear time, O of n. What does that mean? Well, think about finding a name inside a list. Now, if that name is going to be, let's say, the first one, optional, this is the ideal one, then it will take O of 1. But most importantly, you cannot assume that it will be the first element. You must assume the worst case scenario. So it could be in the middle, it could be at third, or it could be at the very end of our list. So you need to iterate through all of the names. Now, think of how we are going to add more data to that list. So if there are 10 elements, you potentially need to go through all of those 10. If we have 100, potentially through all of those 100, and so forth. So this is linearly growing. It will take maybe 1 second if you have 10 elements. It could take 100 seconds for, no, it's just going to scale proportionally to the data amount, to the size of the input data. And that is O of n. That's why we have n, because it depends on the size of the input data. Now, this one, let's just talk about a logarithmic time. So this is quite tricky. But basically, what you are going to do, think about a dictionary and you want to search for a word. What we usually are going to do with logarithmic time complexity, we are going to cut the data, the input size, by half each and every step of the way. So how to search a word in the dictionary? We're going to open up the dictionary right in center and we're going to check, is our word the front part or the end part of our dictionary? And let's say if it's in the first one, we are going to throw away half of our data. Next, again, we're going to cut it in half, take a look at which side our word is, and throw away half the data. And again, half, 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 half. And that way, we are going to go, we're going to get to our initial answer quite fast as time goes by. As you can see, it's just going to cut the data in half. It's just going to throw away all of that. We don't need to worry about iterating through that half of the data as we did with linear time. So that is also kind of really cool. Now think of O of n as speed of light. This could be speed of sound, and this could be a really supercar like the O of n. Now there are also, I just mentioned these two right over here, and the second, I'm just going to go with the worst one on this list, on this chart for now. O of n squared. Now what does that look like in, let's say, in an example? Let's say you have a class of students and you want each and every student to shake hands with each and every other student. Now, if you have 10 students, that would be 100 handshakes. If you have 100 students, it would be like 10,000 handshakes. So each and every element needs to interact with each and every element in the input data. Now, as you can see, as the scale, the size of the input data scales, also the time it requires to go through each and every step will scale proportionally. Think of, if you are coming from a programming background, think of a for loop within a for loop. So you just need to go through the array and each and every element, and for each and every element, you just go through the array once more. Now, this is really bad. That's why I added it as red. Now, there is this also on O of n log n. Now, this is not that optional or performant as O of n, which also, like, if you just want to go through 1 million elements, that's also really time intensive. But we are going to use O of n log n. It's coming from O of log n, but we're just going to multiply it by n, and that's why it sits right over here. Now, I'm not going to go deeper this time right over here. We're going to take it in another lesson or multiple lessons when we are going to talk about sorting, because usually worst case scenario of time complexity for sorting algorithms is O of n log n. Now, there are much more of time complexities, but these are basically what you need to know about. And I have just searched Google for a comprehensive Big O notation cheat sheet, and that's it, bigocheatsheet.com. And please feel free to just take a little bit a look around it. And, we have our data structures, time complexity. There's an average and worst because, you could just be on the worst time complexity and average if some things are set in place. And then there is for space complexity. You always want to look at the worst on the space complexity. And there's sorting algorithms also. You might want to take a look at this. This you don't have to memorize. You don't have to worry about any of this. We are going to talk about all of our algorithms, time and space complexity in each and every episode that is coming up. So make sure, if you like these types of videos and you want to learn about these time complexities on particular interview questions, then go ahead and subscribe. And if you want to ask me, go ahead and check out redeveloper.com.